Alice is letting oxygen go free.
Hello and welcome. We are here at Pier 15 at the Exploratorium on the Embarcadero in San Francisco, and this is the first episode of this year's season of Iron Science Teacher. My name is Julie Yu. I'm a staff scientist and the director of the Teacher Institute here at the Exploratorium, and I will be your host for today's show. Iron Science Teacher is based on an old Japanese TV show, Iron Chef, where chefs compete with a secret ingredient and they try to make a meal. In Iron Science Teacher, we also have a secret ingredient that I will confess is secret to you, but not our contestants. And our contestants, who are staff teachers of the Teacher Institute here at the Exploratorium, they will try to design a science or math activity using that secret ingredient. And so you guys will have the important job of deciding which activity you think is the best and determining who is today the Iron Science Teacher. You guys ready? Let's meet our contestants for today. Our first contestant is teaching the High School Institute at the Summer Institute, our senior scientist, Paul Doherty. Welcome, Paul. Next up, our staff biologist, who is also working with the high school teachers in the Summer Institute, Hillary Osheroff. Welcome, Hillary. Third up, we have a senior science educator who is teaching the Middle School Institute, Lori Lambertson. And last by choice, we have teacher in residence who's leading the Leadership Institute, Zeke Kossover. Here are our wonderful contestants. Contestants, are you ready to reveal this week's secret ingredient, which is underneath this sparkly cloth? Today, we are going to develop science or math activities that use lights. So we have light bulbs, so we have LEDs, fluorescent lights, flashlights. Pick your favorite light source and get busy. The contestants are going to have 10 minutes to prepare their activity that incorporates light. 2015 is actually the International Year of Light, so we are celebrating light here at the Exploratorium along with everyone else celebrating the International Year of Light. So let's see if we can take a look at what folks are doing. Ron is taking a look at Zeke Kossover, who has a light bulb that he has in a socket, and he's trying to figure out where he's going to plug that in. So I wonder what Zeke is doing. He's got the plug. They have to share. You know, the teachers here at the Teacher Institute do work together, even as we engage in serious competition. Zeke is actually a fantastic cook. And so when he's not using science in the classroom, he's using science at home. And we will see if he has a recipe for success today in Iron Science Teacher. We're taking a look at Paul Doherty, who is stringing some Christmas lights on this coat rack here and wondering what he's doing. Paul is celebrating his 30th year teaching the Summer Institute. So we should give Paul a hand. Very nice. Paul is also an avid hiker and rock climber, and we will see if he can climb his way to victory today in Iron Science Teacher. Thank you, Eric Muller. All right, what's going on? We have Lori Lambertson assembling a little, looks like a holiday light, and she's taping it together. Lori also has a lovely light sculpture in her hair, and so she came ready to play. Lori, what's a good thing about Lori? Lori, among her many hobbies, has practiced hula for a long time. And so, you know, hula is a dance where you tell stories, and we will see what moves she pulls out today to tell stories about light. Lori is also a surfer, so when it comes down to the question of if light is a particle or wave, you can probably guess which way she's going to lean. And last but not least, we're taking a look at Hillary Osheroff, who is in... There you go. Hillary is in her very first Iron Science Teacher competition, so let's give it up. She's pouring some things. Hillary also came dressed ready for nice explorations about light. We'll see how light plays out in biology. All right, contestants, so make sure you have everything in place. We're going to start the countdown. Think about what you want to say. Think about how you want to dazzle these good folks in the audience, which actually in the audience today, we have some of the finest teachers, not just in the Bay Area, but around the world. Teachers who are here participating in the Summer Institute. So how's the Summer Institute going, folks? Great to hear. All right, you ready? Lori cleaning up, always a nice thing to do, to have your space prepped and ready to go, whether you're in the classroom or the kitchen. Okay, contestants, that's it. I hope you're ready, because time is up. All right, so I'm going to remind you guys that you have a very important job. At the end of the show, you are going to vote to see who wins the title today. And it is truly bragging rights in the office of who wins the title of Iron Science Teacher. So pay attention. Think about what activity you like and who did the best presentation, and you will vote by your applause at the end. So first up, we want to welcome our senior scientist, Paul Doherty.
So I learned that the secret ingredient was lights. And I thought back to the time that the Exploratorium sent me to Sweden in December. And I knew it was going to be dark. And I knew that I had to find some way to find the keyhole to get into my apartment. And I looked around and I discovered light-emitting diodes had replaced flashlights. These are wonderful little pocket lights. You can carry them everywhere. And all of a sudden, let there be light. But this one was a special one. And it actually, if I blink it, set it twice, it has a dim setting. And you may think, well, dim setting, big deal. But while it was on dim, I happened to move it. Do you see what it's doing? It's blinking on and off. Well, I'm a physics professor. And if you give me something that's blinking, I think strobe light. And what can I do with a strobe light? Well, since you asked, I can take a strobe light and turn it on this blinky mode, and then I can see what happens when I swing it around. And you might see the little blinks of light up there going around. And if I go slow, they're close together. And if I go fast, they're far apart. And if you're going to think about motion, since this light is blinking, and it turns out, I'll tell you later, it's blinking 100 times a second, almost exactly. So when you see it go that far, that's the distance it's going in 100th of a second. It's going fast. And when the blinks are that far apart, it's that far it's going in 100th of a second, it's going slow. So this lets you see speed. It goes from speed, which is, if this were just plain on, just on, I'd have analog speed. It's just a smear. This is what you do around the fire. You know, in the summer, you take the stick and you put it in the fire and you get it glowing and it zips around and it just kind of makes this track of continuous light. Oh, that's even better, okay? And I recommend you do that, but don't burn yourself in the fire. But then when I put it on blink, I go from analog to digital. I get digital blinking. And I can make it go faster. So that was, oh, there we go. I thought, oh, that's wonderful. And so thinking about that, by the way, you can actually get these. They're called iNova microlights. You know, they're really expensive. They're strobe lights. You can do things with strobe lights. And there I was. I swung it around in a circle. You can see how it's going. I immediately thought of what to do with it. You put it on a baseball bat and measure the speed of the baseball bat. I didn't bring a bat for today, but as a physics professor, I knew the experiment I really wanted to do. I remembered Galileo. And what Galileo did was he went up the Leaning Tower of Pisa with a cannonball. Well, I didn't have a cannonball, but I'm going up, and I don't have the Leaning Tower, at least I hope not. and he dropped the cannonballs, 2 cannonballs, to see how they fell. I'm going to do this a couple of times. So watch the light itself. And, oops, sorry, just a minute, I'll make sure it's on the blinky mode. Well, bright blinky, there we go. And see if you can see it blinking on the way down. You see it blink? Somebody hand that. Could I have a child down the bottom to help me out? You want to grab that for me? And hand it up to me? Thank you so much. You ready for it again? Okay, this time that over there, watch it go down and watch it blink as it goes. Okay, oh, thank you. Oh boy, I really need to reward you. Okay, over here, people, see that? Watch it, here it goes. Blinky. All right, so, oh, thanks, 2 helpers. So there, I had just reproduced Galileo, and I thought, well, I'm doing pretty good here. I'm actually doing pretty good. I wanted to actually measure how fast it was blinking, and I realized that what I wanted to do was to convert light into sound. So what I have here is a solar cell, and a solar cell converts light into electricity. And a speaker converts electricity into sound. So what I can do is I can take one of my blinky lights right here, and you can hear it's blinking. You can hear it blinking. If I put it on solid, there's no blink. I can make it click. So I can hear the blink. And I found that different lights have different pitches of sound. So I can hear the frequency. And I measured it, and that's how, by measuring that with a frequency measurer, that's how I found out that these blinked at 100 times a second. Well, that was good. I thought, okay, I got the light. I got it moving in a circle. I went from analog to digital. I'm really on a roll here. And then I sat down again. I looked around my house. I looked at my Christmas tree. It's June. My Christmas tree was looking a bit sad. It has a lot of lights on it. Ooh, I wonder what I can do with Christmas tree lights. I'll harvest the Christmas tree lights. These are light-emitting diode Christmas tree lights. And I'm going to have my lovely assistant, Eric, come up. This is Eric Muller, also a teacher in the Teacher Institute. You can grab the end. Well, it turns out that these lights are blinking too. And now you know how to see blinking lights. When I move them in a circle, if they blink on and off, you know they're blinky lights, okay? And if I go faster, the lines get longer. And if I go slower, they get closer together. And then, but immediately seeing them go around like this, I thought, oh, that was the fundamental oscillation of a harmonic resonator. That's what a physics professor does. And I can go for the second harmonic, otherwise known as double Dutch for those of you that do jump rope. Okay. And then I got carried away and thought, oh wow, I'm so much on a roll here. I could do 3 of them. Oh, it's really hard. Almost. Okay, so I gave up at 3. So next time at your Christmas tree, it's after Christmas, it's sitting there, it's looking forlorn. Think about taking off the light bulbs and spinning them around. But that was a good thing to do so I could study the physics. I thought, you know, there's another physics problem with light bulbs. You can, thank you, Eric.
Come on, Eric Muller.
Is that, you know, sometimes they show these old cowboy shows and the cowboys are there with their lariat. Well, now I've got a digital blinking lariat. And I can make this go around in a circle, and that was kind of dull. But there's other patterns you can make. You can make a pattern like this. And you see the blinking, and you get the entire pattern. That's called the next harmonic of this. And then I thought, just like going for 3, maybe I can go for the next pattern. And that one has 2. Yes! I actually managed to make that. So now, at the end, not only do I have, somewhere here, not only did I have baseball, I had Galileo's experiment, dropping the lights and watching them blink. And I had what you can do with Christmas tree lights. And I saw some of you taking photos with your cameras. If you actually do this and record it with a camera, look at what you get. This beautiful three-dimensional array of lights. So go forth, grab lights, make them blink, and swing them around.
Thank you. Folks, that was Paul Doherty with the physics of blinky lights. Trust the physicists to come up with a great demo about light. Next, we will see how a biologist approaches this problem. Please welcome Hillary Osheroff.
All right. So, I'm a biologist. I have to be honest, I'm not super interested in light bulbs that need to be plugged into an electricity source to light up, because there are living things that also create light that I think are much cooler. So when the living thing produces light, it's called bioluminescence. There's lots of things that bioluminesce. There's bioluminescent jellyfish. There's bioluminescent bacteria. All kinds of invertebrates in the sea and fish in the sea bioluminesce. There are even bioluminescent mushrooms. But you may have guessed from my outfit that my favorite bioluminescent creature is a firefly. So when organisms are bioluminescing, when they're glowing, they're usually signaling to each other. They're saying, come over here and mate with me, or come over here and let me eat you, or both of those things sometimes. There's fireflies that do both of those things. They're really rad. So I'm going to show you how a firefly lights up. Unfortunately, we're in California. There are no fireflies. That was going to happen. Rookie, sorry. Okay, so there's no fireflies in California. It is a sad thing about our state. So I had to make a firefly. Here's my firefly. The part of the firefly that lights up is the last segment of its abdomen, which is down here. It's called the lantern. It's like where a firefly's butt would be if a firefly had a butt, which it doesn't. And the firefly's lantern has cells that contain a molecule called luciferin. Luciferin is a molecule that it will react with oxygen in the lantern in an oxidation reaction, and the oxidation reaction will give off light. So you can actually buy luciferin from a chemical supply company, but it's really expensive. My firefly is kind of huge. So I'm going to use something different, but that works in a really similar way. This is a chemical called luminol. And it does almost the same thing as firefly luciferin. It's going to react with oxygen, and it's going to give off light. So I'm going to fill up my firefly with luminol. Okay. So in a real firefly, the oxygen for this reaction is going to be just regular oxygen gas, O2, same thing that we breathe. For this reaction, I have to use something a little bit different, oxygen in another form. This is sodium hypochlorate, NaOCl. You can call it bleach if you want to, same thing. So when I add oxygen to the luminol in the firefly's lantern, it's going to give off light.
And so, Hillary, you're making light, and we should probably dim down the lights that are in the webcast
Yeah,
studio.
so good point, Julie. Turns out fireflies, really, they only come out and glow at dusk, at night, when they come out to like try and find a mate. So if we could take the lights down a little bit, this will all look a little bit better. I've also put my firefly in a cozy little box to make him feel more at home. Okay, ready to watch this firefly light up? Okay. Ah, thank you, thank you. He's going to glow for a little while. It doesn't last too long. So when you think of reactions that give off light, those reactions very often give off a lot of heat too, right? As energy. They are, like a flame is going to give off a lot of light, but tons of heat. It loses a lot of energy as heat, right? A light bulb gets really hot too. Even like an LED, which is supposed to be very energy efficient, it's going to get a little bit warm. Do you think that my firefly's lantern gets warmer when it lights up? Let's find out. Can I get a volunteer from the audience to monitor the temperature of my firefly? How about you? Come on down.
Hi, volunteer. Tell me your name.
I'm Dorothy.
Dorothy, what brings you to the Exploratorium today?
I'm in the Teachers Institute.
Yay!
Dorothy, where and what do you teach?
I teach 6th grade math and science at Livermore.
Great. Thanks for helping us out.
All right. So Dorothy, could you just put your hand on the Firefly's lantern, tell me how it feels.
It feels like room temperature.
Room temperature. Can you check the thermometer? Can we give us a reading?
22
22 what?
degrees Celsius.
22 degrees Celsius. Units are important. All right, let's light up this firefly and see if the temperature changes. Ready? Woo. All right, still glowing. Dorothy, can you just put your hand here and tell me how it feels?
Feels the same.
The same. Can you check the temperature?
It's still 22 degrees Celsius.
22 degrees Celsius hasn't changed at all. Thank you very much, Dorothy.
Thanks, Dorothy.
So, bioluminescence it's a cold light. It's incredibly energy efficient. It loses almost no energy as heat. And there are scientists out there who are working on putting the genes that control these reactions in fireflies into trees so that someday, maybe instead of street lights that use a ton of electricity on our streets, we will have bioluminescent trees lining our streets. So that is how a firefly finds a mate without burning off its butt. Thank you.
Great. Thanks, Hillary. That was bioluminescence, or making light through chemical reactions. Great. Next up, we have our senior science educator, Lori Lambertson.
Hello, everyone. Well, during the building phase, when you saw that I was rapidly building away, wow, it's crunchy over here. I built a device that's going to help me measure salinity. And that's how I'm going to use some light today. But because I'm talking about salinity, I thought maybe we could talk about other ways that we can detect salinity. What's a normal way that you might detect salinity? By tasting it, right. And we've been studying perception today in the Teacher Institute. And so I want to show you how we're going to talk about salinity and tie it into perception, biology, physics, and earth science, and mathematics.
No way.
And I'm what? I'm going to come up to the center. I have some helpers that were going to help me pass out my trays. So these are color-coded cups. There's a purple-rimmed cup, a blue-rimmed cup, and an orange-rimmed cup. Ideally, you'll take one of each and try and determine which one you think is the saltiest or the least salty. And then we're going to talk about where in the bay you would find that sample. These are not bay water. I made these out of tap water in my kitchen with salt from my kitchen. So, who wants to try my little taste test while I get my other things set up? I have another tray. So my volunteers from the class, these are teachers from the Teacher Institute, are going to help set that up. And I'm going to set up my other thing here. Oh no, go ahead, taste away. See if you can figure out which one is the saltiest.
How does it taste?
Really salty.
Really salty.
I don't really like it.
I don't
Pretty
either.
salty.
I don't really like it. What a great quote.
So we're trying to figure out which of the three samples is the saltiest.
Yeah, so I color-coded them. So you're going to tell me by color which one you think is the saltiest.
Who else is trying one of these? How does it taste?
This one tastes salty.
Yeah, which one is that? That one is uncolored. Oh no, blue in color. Are the others salty as well?
All right,
which one's the least salty?
I have no idea.
We're about to find out.
So, guess what? I color-coded the bottles too, because I can't remember anything. So, of these three colors of water you tasted purple water, orange water, and blue water. Which one was the saltiest? Purple. We have a vote for purple. Anyone else? Blue. Blue water. More people think blue. Blue is the saltiest. And so anyone think orange was the saltiest? So orange was the least salty. So I got some data from the internet about the salinity of the bay, and I matched the salinities in these bottles to 3 locations in the bay. One of them was up here at the Carquinez Straits. One of them was here at China Camp, and one of them was here right by the Golden Gate Bridge. Which one do you think is saltiest? The one by the Golden Gate Bridge, yeah, the blue sample. And which one is going to be least salty? The orange one, right, because that's up by where we get our fresh water flow into this estuary from the Sacramento-San Joaquin rivers flowing through the delta. Good job, everybody. So we can do something with salinity using our sense of taste. But today's secret ingredient was, oh gosh, I forgot, light. So I built a conductivity meter to measure salinity. What? Conductivity, salinity? Oh, if we could do the next slide, I'll show you where I got my data. Because, oh, that's not the one I expected. That one, yeah. So Syncus is a Bay Area organization that collects data about weather and water, and it's great live data. It's fantastic. So I have a conductivity meter here. I took a light and I stuck it to a battery, and one terminal of the battery is attached to the light, and the other terminal of the battery is attached to one of these nice aluminum probes. So I have 2 probes coming down, and I have different salinities of water. 0 ppt. ppt? What the heck is that? That's parts per thousand. So it turns out the ocean, average ocean salinity is 35 parts per thousand. So I made these little models of ocean water out of rice. And out of 1,000 grains of rice, 35 of them are colored blue. So you can check this out and see what it looks like to be only 35 parts per thousand. When you guys tasted that salt, it probably tasted pretty salty. Even the orange solution. Well, it turns out that orange solution was 22 parts per thousand. Not as salty as the ocean. The China Camp data, the purple one, was 27 parts per thousand, and the Fort Point one, the blue one, was 33 parts per thousand. Average ocean is 35 parts per thousand. So I have some different parts per thousand in increments of 10 ppt, and I'm going to see what happens with my conductivity meter. I'm going to start with 0 parts per thousand. Oh, broken conductivity meter. Happens every time in Iron Science, teacher. Wow. So that's 10. 20. Anyone see a change? 30. 40. Cool, huh? So what's going on? Why is these are different amounts of salinity, and yet what we're seeing is a change in the brightness of the light. If I could have the next slide, please. So what's going on with my conductivity meter is the salt in the solution is going into the ions, Na, sodium, and Cl, chlorine, and they are separating and going to opposite sides of these 2 probes, and it's like they're completing the circuit. And so more ions make the circuit complete more effectively. If I just do this, I can complete the circuit. Sure. If I just touch, yeah, I burned that one out. That's why I bring more than one of these. Just bring out a spare. So when I touch the 2 metal pieces together, yeah, of course, I complete the circuit. But these 2 pieces aren't touching in the water. It's the ions in the water that are helping me complete that circuit. And the more ions in the water, the brighter it gets. That's cool. So it turns out we measure this here at the Exploratorium. We have CTDs in the water. Oh, I'm sorry. Can we do the next slide? More ions in the water, brighter light. Sorry. So these are deployed in the water. They have little instruments in them that look like this to measure. CTD stands for conductivity, density, and temperature. These are very commonly used in ships and on piers to measure salinity in the ocean. One of these is one of the little probes that's in here, and it has some similarities to this probe. What do you notice about this probe? Two parallel metal things. If you look down inside here, there are two parallel metal things. I'm going to pass this around and you can look down inside there. This thing costs $500.
Don't drop it.
It's broken. Do whatever you like with it. This thing costs about the price of a 9-volt battery. Maybe $1. So, who cares? Why are we measuring salinity? Why is salinity important? It turns out we use another kind of light to measure global ocean salinity. NASA has launched a satellite called Aquarius. And Aquarius circles the globe once every 7 days and can draw this map of ocean salinity. The redder the color, the more salty the ocean. Scientists are really interested in this because where we see higher salinity, there's more evaporation. Where we see lower salinity, there's more precipitation or runoff from the land. So this ties us into the global water cycle. Also, salinity in the ocean changes the density of the water. And density is what drives ocean currents. And that's how heat moves around in the ocean and on the planet. So understanding the global water cycle and understanding global ocean circulation helps us understand how our climate is changing. So understanding global ocean salinity is a way that we can help understand what's happening on our planet. The oceans are getting less salty as ice is melting because temperatures are warming. So this is a really new satellite. It's only been in the sky for a couple of years, like 2009, I think. And so, but look, this is May's data, May 2015. I love the internet. So, here's my big mystery. I have a sample of bay water here. It really is bay water because my teacher saw me take it out of the bay yesterday. And I don't know the salinity of it. I didn't measure it. But I have my conductivity meter. So you guys are going to use your eyeballs and tell me which of my known samples this matches. Ready? Let's take a look. Bright, not kind of bright. Same? Compared to the 30? People are like, eh.
Close.
Close. 20? No. So greater than 20? As high as 40? Nah, people up close are like, nah. So maybe about 30? Yes. So we've just measured the salinity of the bay using a $1 instrument. Thank you. That's salinity.
Thank you. That was Lori Lambertson and using light to measure salinity through conductivity. It is kind of crunchy here. It is crunchy. Thanks. Last but not least, we have our teacher in residence, Zeke Kossover.
So hi. I've noticed that an interesting thing is happening with my students. One of the things that I used to teach a lot about in physics class was using about how light bulbs worked, because incandescent light bulbs were really easy to understand. Now that we're using more and more fluorescent lights and LED lights, my students don't understand what incandescent lights even are very well anymore. And so it's become important for me to teach them what this old school terrible technology is so that they won't just think I'm an old fogey and know stuff that they don't know. So let me show you one. So I'll plug it in. And we can turn it on. Here's the light bulb. Inside of there, there's a very hot wire that electricity is running. Well, it was a cold wire to start with. Then electricity ran through it, and now it's a very hot wire, and it's letting out light. A question that my students ask almost right away after they see this is, why the glass? Why is there this bulb around that hot wire if there's a hot wire inside of there? And so I usually solicit ideas from my students. And the most common idea that they tell me is that you wouldn't want to get burned on that very hot wire. And I thought about that for a moment, and it is true you would get burned on it. But it actually turns out that light bulbs were invented before lawsuits. And so that's not the actual reason. The actual reason is that the wire on the inside there, the tungsten wire, actually gets so hot that with the oxygen in the air, it would catch on fire. It would burn. And so instead, inside of this little glass casing is an atmosphere that has no nitrogen in it so that the wire can't catch on fire. And my students were like, whatevs. Because they just didn't believe me when I was telling them that story. And they were like, I would like to see some way for us to actually find out if that was true. So I thought to myself, I wonder how I'll do that. And then I had an idea. So I thought to myself, what if I were to take off this glass in some way and then put it in a place where there was no oxygen so that we could see that it would still light up if there was no oxygen there? And so I needed something that didn't have any oxygen at all. And it turns out that there's a product that is completely devoid of oxygen. That product is liquid nitrogen. I like the cheer for liquid nitrogen. It's a good crowd that cheers over liquid nitrogen. So liquid nitrogen is an incredibly cold liquid. There's classic demonstrations you can do with it, like you put a flower into it. We'll change all the flour's water to ice, so that then we can smash it. I actually feel really bad smashing a symbol of love on a day like today. So please, later on.
What a guy.
Here. So liquid nitrogen is fantastic because it has no oxygen in it, and it doesn't conduct electricity. So like Lori said, if something has salt in it, then it can conduct electricity, but salt won't dissolve in liquid nitrogen, so it's a almost total non-conductor. So it's the perfect place for us to examine this. So I'm going to pour myself a little bit more, because if a little is good, more is better. And now we'll take the globe off of this.
Hillary can probably help you with that.
Ooh, sorry, that was supposed to go in the box. All right, so we still have the light bulb, the filament is intact.
See it?
Can you see it?
Can we see it? Let's see. Yeah, we can sort of see it.
Great. So the filament is still intact. This switch was turned off the last time I used it.
Can I give you a hand?
So I'm going to turn it on now. Of course, it's still not plugged in, so everything's fine. What I'm going to do now is I'm going to dip this filament into the liquid nitrogen, and Julie here is going to plug it in, and we'll see if it can still glow underneath the liquid nitrogen. Should we clean this off just a little? A little ice there. Sorry about the glass. All right, ready? All right, let's plug it in. So you can totally see that it's perfectly happy just continuing to burn there underneath the liquid nitrogen, because it's not burning. It's just glowing there and doing its own thing. The filament heats up the liquid nitrogen so much that it boils it away, leaving a little gas of nitrogen. Now, if I bring it out into the air, the oxygen will combine with the filament, and Tinkerbell will die. So y'all ready for that? So now you know what happens on the inside of one of these old school filament light bulbs, so that you'll know something that the old folks know too.
Fantastic. That was
Thank you
Zeke
very much.
crossover with how an incandescent light bulb really works. That was great. Can we give everyone a round of applause? We're going to bring out our 4 contestants, and then you guys are going to vote. I'll remind you what they did, but you will vote by the strength of your applause for who you think should be crowned today's Iron Science teacher. So let's bring them out. We have Paul Doherty, Hillary Osherov, Laurie Lambertson, and Zeke Kossover. I'm going to remind you that Paul showed us physics with blinky lights, and Hillary taught us about bioluminescence, the light that life makes. Laurie used light to measure salinity, and Zeke showed us what happens inside an incandescent light bulb. So are you guys ready to vote? We've stepped up our game here at Iron Science Teacher. I have a sound level meter that I'm going to measure the strength of your applause to avoid any complications in the office. So let me turn this on. And let's hear for Paul Doherty. How about Hillary Osherov? Laurie Lambertson. And Zeke Kossover. The first Iron Science teacher of 2015 in her rookie appearance, Hillary Osherov. That's it, folks. Thanks so much for coming out to watch a show. Next week, we will be at a special date and time. It will be Thursday at 1 p.m., where teachers who are participating in our Teacher Institute will step up and compete in the didactic duel of Iron Science teachers. So come check them out. Have a great day at the Exploratorium.